In this video we're going to talk about Newton's law of motion, and there's 3 laws that we're going to go over. Let's talk about the first law. So what exactly does Newton's first law of motion state? Well, one part states this: an object at rest will remain at rest unless acted on by a force, particularly an unbalanced force. So let's say if we have a surface and if there's a box on a surface, if we don't apply a force, this box will not move. All the forces that are currently acting on this box cancel their balanced forces. For example, you have the weight force of the box. Let's say the box has a mass of 10 kilograms. To calculate the weight force, it's equal to m times g. M is the mass in kilograms. G is the gravitational acceleration, so m is 10 kilograms, g is 9.8 meters per second squared. That is the acceleration due to gravity, so the weight force is simply 10 times 9.8, so it's equal to 98 newtons. Gravity exerts a downward weight force on any object. Now the block is not accelerating downward, it's at rest, so there must be some other force that keeps it at rest. The force that the ground exerts on a box is known as the normal force, and it has to balance the weight force in order to keep the block where it is, and so the normal force is also 98. So as you can see, these are balanced forces. The net force on this box is equal to 0, and so it remains at rest unless we apply an unbalanced force. Then the block may begin to move. We may have to overcome static friction, but if we apply force, then it can move. So an object at rest will remain at rest unless acted on by net force. So that's the first part of Newton's first law of motion. Now what about the second part of it? Newton's second law also states that an object in motion will continue in motion unless acted on by a net force. It's basically a statement of the law of inertia. Now let's think about this. Let's say if we have a surface with, let's say, a rough surface. Let's use a carpet for example. If you try to roll a ball on a carpet, for the most part the ball is going to quickly come to a stop. It's not going to move very far, and the reason why that happens, even though this object is in motion, there's a lot of friction between the surface of the ball and the carpet, and friction opposes motion, and so because there's a net force, this object will not continue it in motion. It's going to come to rest, and that's what we see in real life. If you roll a ball, eventually comes to a stop. It doesn't continue forever, but Newton's first law of motion states that an object in motion will continue in motion unless acted on by force. Now if you think about it, what will happen if we can get rid of friction? Will the object continue to move forever? Now imagine if you have a smooth surface, let's say like ice. Now if we take a puck and slide it across the ice, it's going to move for a very large distance. It's not going to come to rest like the ball on the carpet. The ball on the carpet is going to stop after a very short distance, but this puck is going to slide across the ice for a long time. Now let's say if we use a ball and we roll it on ice, let's say if you put it on a frozen lake and you roll it across the lake, it's going to roll for a very long time until it comes to us. It's going to take a long time for it to come to us. Now why is that? Why is it that if we roll a ball on a rough surface, it takes a very short time to come to us? It comes to stop, it comes to a stop quickly, but if you take a ball and put it on an icy surface, it will roll for a longer time. The reason for that is because there's more friction between the ball and the rough carpet, but between the ball and the icy surface there's less friction, and so because there's less friction, this ball will continue to travel for a much longer time. Now what's going to happen if we can completely get rid of friction? Will the object continue to move forever? Think about it now, keep this in mind. Even though there's very little friction between the icy surface in a ball, you also have air resistance as the ball is moving forward. The air molecules can slow it down, so you have air resistance. And if it's moving fast, this can be air drag as well. But where can we find a place where there's virtually no friction? The best place where this almost no friction is outer space. In outer space there's virtually no air. It's almost non-existing. You might have a few molecules here near, but for the most part the pressure is extremely low. If you think about it, we know that the Earth revolves around the Sun, and the Earth is an object in motion. And the Earth has been revolving around the Sun for a very long time. Millions, perhaps billions of years, and it continues to keep moving, and it makes sense because in space there's virtually no friction. It's not enough to slow the Earth down, and so it continues to move into orbit, and thus we can see Newton's first law of motion in action. Here an object in motion will continue in motion unless acted on by a net unbalanced force. Now you might be wondering, all this information is great, but how I apply this information in the problem? How will I see a question on a test? Well, there's some things that you need to know. If an object remains at rest, then that force acted on the object is equal to 0. Make sure you understand that constant. The second thing is, if an object is in motion, let's say if it's moving with constant velocity, then the net force acting on that object is equal to 0. Make sure you understand that if the net force is not 0, then there is a net acceleration, but when the net force is 0, the acceleration in that direction is also equal to 0, which means that the velocity is constant k. Combined acceleration is defined as the change in velocity, that is the final velocity minus the initial velocity, divided by the change in time. So our constant velocity Vf and Vo will be the same if you take a number and subtract it by the same number. You're going to get 0. So in constant velocity, Vf minus V0 is 0. 0 over t is 0. Now according to Newton's second law, the net force is equal to the product of the mass and the acceleration. So if the acceleration is constant, and if you increase the mass of the object, the net force will increase. So the net force is proportional to the mass of the object. Now let's say if you keep the mass constant and if you increase the magnitude of the acceleration, the net force will increase as well. So the net force is also directly proportional to acceleration. Now what if we keep the net force constant? What is the relationship between the mass and acceleration? If you increase the mass, the acceleration will decrease, provided if the force remain is the same. If you decrease the mass, the acceleration will increase under constant force conditions. Now let's put some numbers to it. If you double the mass while keeping the acceleration constant, what effect will it have on the force? By what factor will the force increase by? To answer these questions, simply plug in the values. If you double the mass, replace it with 2. If the acceleration is held constant, replace it with 1, so the force will increase by a factor of 2. If we triple the mass and keep the acceleration constant, the force will increase by a factor of 3. Now what if we double the acceleration and triple the mass? What effect will it have on the force? So if you triple the mass and double the acceleration, 3 times 2 is 6, the force will increase by a factor of 6. If you quadruple the mass, triple the acceleration, the force will increase by a factor of 12. So Newton's second law basically states that the net force is equal to the mass times the acceleration. Now you can also describe Newton's Second law of motion using something else. So let's start with the equation F is equal to ma, that is the net force is equal to the mass times the acceleration. Now we said that the acceleration is the change in velocity v final minus v initial, which we can write as delta v. The triangle represents change is the change in velocity divided by the change in time, so delta v over delta t is the same as saying v final minus v initial over t, where does t represents the change in time. Now what is mass times velocity? Mass multiplied by velocity is equal to momentum, indicated by the symbol a. Lowercase p. Momentum is mass in motion. An object at rest has zero momentum. An object that's moving has momentum. So let's say if here's a question for you. Which object has more momentum, a car moving at 30 miles per hour or a train moving at 30 miles per hour? If both objects are moving with the same speed, then the one that has more mass will have more momentum. The train has a lot of momentum. It's very difficult to stop a train. It's much easier to stop a car than a train, so momentum is the product of mass and velocity. So an object with a lot of mass and with a lot of speed has a lot of momentum. Now if mv is equal to p, then that means that m delta v has to be equal to delta p, that is the change in momentum. So let's replace this term with delta p, so we could say that the net force is equal to the rate of change of the momentum with respect to time. So this is another variation of Newton's second law. The net force is the change in momentum divided by the change in time. By the way, if you start from this equation and if you multiply both sides by delta t, you're going to get another important theorem. The force multiplied by the change in time is equal to the mass times the change in velocity. The product of the force and the time is known as input, and mass times the change in velocity is known as the change of momentum. So this is known as the impulse momentum theorem. The impulse is equal to the change in momentum. Now what about Newton's third law of motion? What exactly does that state? The third law states that for every action there is an equal and opposite reaction. So Fa is equal to negative Fb. So if you apply a force, there's going to be a reaction force applied to you. Both forces will have the same magnitude, but the direction of the two forces will be opposite to each other. So let's go through some examples. Let's say if a person jumps in the air and throws a basketball, as the basketball moves in that direction, he applies a force on it. But he also, while in the air, he's going to move back, so there's like a recoil force applied to him now, because the mass of the ball is less than the mass of the person. The ball is going to travel a further distance away from the person because the ball will experience a greater acceleration. Remember, for the same force, if you decrease the mass, the acceleration increases. These two are inversely related, but the force exerted on the ball and on the person is the same. So let's put numbers to this so you can see how it works. So let's say the ball has a mass of 2 kilograms and the person has a mass of 80 kilograms. Actually, let's say 100. 100 is a nice number. Now let's say that the person applies a force of 200 newtons on a ball. The person is going to feel a reaction force of 2 hydrogens in the opposite direction. Now what is the acceleration of the person and the ball? Now we know that according to Newton's second law, F is equal to ma, so the acceleration is the force divided by the mass. So if we take 200 divided by 2, the acceleration will be equal to positive 100 meters per second squared. Now for the person, 200 divided by 100 is only 2, so the acceleration is negative 2 meters per second squared. Acceleration is a vector and vectors have magnitude and direction because the person feels a force directed towards the left. His force should be negative, and therefore his acceleration is negative. Force and acceleration and velocity are vector quantities. The direction is important. Speed is a scalar quantity. Speed has magnitude only, but as you can see, the object with less mass experiences are much larger acceleration. The person with more mass experiences a smaller acceleration. However, the forces are equal according to Newton's third law. For every action force there is an equal but opposite reaction force. Now here's another situation. Imagine if you are in the ocean on a boat. Let's say this is you and you have a ball in your hand. Now I want you to imagine a situation, so just think of yourself being on a boat in the ocean. And if you throw the ball towards the right, what do you think is going to happen to you and the boat? In what direction will you move? Now intuitively, you know that if you apply a force to throw the ball towards the right, you're going to feel a force that's going to push you and the boat towards the left. But because the ball has less mass, it will have a greater acceleration, and so it's going to travel a greater distance. Now because the combined mass of you and the boat is so much more larger than the ball, you won't feel the acceleration as much. You might move a little, but the distance that the boat moves towards the left is insignificant towards the right. But it doesn't move according to Newton's third law. For every action force there is an equal and opposite reaction force. Now let's go over in one more example. So let's say this is the Earth, and over here we have the Moon, which is much smaller than the Earth. Now let's say you're an astronaut somewhere in space and you have a ball in your hand. Okay, let's redraw the picture. My drawing is terrible. I didn't want to draw the stick figure too big, but sometimes bigger is better. So this person has the ball on his hand. Now he's in space, flown in space. Imagine if you're this person and you're floating in space. Now you don't want to drift deep into outer space. You want to get back to planet Earth. In what direction should you throw the ball now? Remember, you want to throw the ball in a certain direction so that you will be accelerated towards the Earth. So here are your options. Do you want to throw the ball in this direction towards the Moon, towards the Earth, or above you? Where should you throw the ball? Now if you throw the ball, let's say towards the Earth, you are going to feel a force that's going to push you towards the Moon, which is not where you want to go. If you throw the ball south with you, you're going to feel a force that's going to push you away from the Earth. And the Moon may be towards the Sun, which is not good either. So what you want to do is you want to throw the ball towards the Moon, because if you throw this way, you're going to feel an opposite force that will push you this way, that is towards the Earth. And so once you throw the ball away from the Earth, you can feel the force that's going to push you towards the Earth. And while you're in space, there's not much restriction, so the velocity that you acquired as you throw the ball towards the right, that velocity will remain constant, and so you'll slowly fall towards the Earth, getting back to where you belong. So understanding that principle can help you to travel in space. If you want to go towards the Moon, throw the ball towards the Earth and you're going to be pushed towards the Moon. So basically, whatever direction you want to go, throw the ball opposite in that direction. So if you want to go north, throw the all selves. If you want to go yes, throw the ball west, and vice versa. So now we're going to work on some problems. Feel free to pause the video and work on each problem that you see. From this point on, a car travels on the road with a constant velocity. What is the horizontal net force acting on the car? So what do you think the answer is to that question? What is the net force now? If you recall, any time an object is moving with constant velocity, then that force is always equal to 0. Now what about the acceleration of the car? Well, according to Newton's second law, F is equal to ma, so if the force is 0, the acceleration must also be equal to 0. Now part C, if the frictional force acted on the car is 500 newtons, and what force is applied to the car by the engine? So let's draw a picture. I'm just going to draw a box because it's easy to draw, and this box represents the car. So let's say the car is moving to the right, so V represents the velocity where it's going. Friction opposes motion, so the frictional force is 500 newtons. Now the net force is 0, which means that the applied force has to be 1500 newtons. These two forces cancel out, so the net force is 0, and therefore the acceleration is 0. And if the acceleration is 0, the velocity is constant. Keep in line, acceleration is the rate of change of lossing. If the velocity changes, then there's an acceleration. If the acceleration is 0, the velocity will not change. A force of 200 newtons is applied on a 10 kilogram box across the frictionless surface that is a horizontal frictionless surface. What is the acceleration of the box? So let's draw a picture, and here is the 10 kilogram box, and we're going to apply a force of 2 hydrogens. So to calculate the acceleration, we can use this equation. F is equal to ma, so F divided by m is a. The force is 200 newtons, the mass is 10 kilograms. 200 divided by 10 will give us an acceleration of 20 meters per second squared. Now what about part B? If the box accelerates from rest, what will its final speed be? After 8 seconds, the acceleration tells you how much the speed changes every second. So let's make a table. So initially the velocity or the speed is 0. Every second that passes, the speed will increase by 20, so 1 cycle later is going to be 22 seconds. Later 43 seconds later, 64 seconds later, 80, and I'm going to continue the table. Here let's see if I can fit in 5 seconds later. It's going to be 106 seconds later, 127 seconds later, 148 seconds later, 160. So after 8 seconds the speed of the box will be 160 meters per second. Now the equation that you can use to calculate this answer is this equation. We're looking for the final speed Vf. The initial speed Vo is 0. Because it started from rest, the acceleration is 20. The time is 8. 20 times 8. If you have 8 $20 bills, how much money do you have? 8 $20 bills is 100. So 20 times A is 160 C at 160 meters per second. Now what about part C? How long will it take the box to reach a speed of 500 meters per second if it continues to accelerate at this ring? So start from a speed of 0. A is 20. Let's solve for t. The final speed is 500, so we got to divide both sides by 20. So what is 500 divided by 20? Well, we can cancel a 0, so it becomes 50 divided by 2. Half of 50 is 25. So it's going to take 25 seconds for the box to accelerate from rest to a speed of 500 meters per second. A force of 300 newtons is applied across a 20 kilogram box. The frictional force acting on the box is 200 newtons. What is the net horizontal force on the box? So let's begin. So we have an applied force of 300 newtons, so let's call it a capital F, and there's a frictional force of 200 newtons, so then that force is in this direction. Then that force is simply the difference between the two forces, so it's 100 newtons directed towards the right if these two forces are in their respective positions. Now what is the acceleration of the box? Once you have the net force, you can use this equation. F equals ma. It's a fine acceleration, so the acceleration is in that force of 100 divided by the mass of the box, so the acceleration is 5 meters per second squared. Now what about part C? How far will the box travel after 12 seconds if it continues to accelerate at this rate? Starting for us, so the initial speed is 0. If it starts from rest, the time is 12 seconds. Our goal is to find the distance traveled, so we're looking for d. What equation has v? Initial TDMA, so make sure you review your kinematics equation. You never know when those equations will be helpful. The equation that you need is the displacement is equal to the initial speed multiplied by the time plus 1/2 a teaspoon to 0. The acceleration is 5 and the time is 12, and let's not forget to square, so we have 1/2 times 5 times 12 times 12. 1/2 times 12 is 6. 6 times 5 is 30, and 30 times 12. If we multiply 30 by 10, that's 330 times 2 is 60, so 30 times 12 is 360. So this particular box is going to travel 360 meters before it's going to travel 360 meters in 12 seconds. That's